adults here. So let's go on to, we're going to look a little bit at the metric system. And then we're going to go on and introduce that first lab, which is about variables. Okay, so metric system. Okay, so hopefully everybody is seeing this giant picture here of a galaxy. And the idea is that, yeah, in science we measure really big things. Okay, so we're going to talk about the units of length, mass, and time, a little bit about area and volume and scientific notation, and eventually probably we'll cover some stuff on dimensional analysis, significant figures, and converting units. Luckily, this class doesn't have a lot of converting units. That's one of the nice things that the author did. If the question is in meters and seconds, you use meters and seconds. But if it's in centimeters and seconds, you use centimeters and seconds. And if it's in feet and seconds, you just use feet and seconds. So you don't have to go around converting everything into meters. Be reassured, that's one of the very nice things. So we're not going to cover much converting units because basically you have very little conversion of units in this course. Okay, so the lengths for length, mass, and time are the basic units for the metric system. And all the other units, like newtons, or you might have lumens of light, or watts of power, those are all actually combinations of length, mass, and time. And the basic fundamental unit, the first one they came up with really was the meter. And when were they doing this? Well, this was happening during the 1700s, especially as people were getting rid of their kings. So think the revolution here in the United States, and also what happened, the French Revolution. And they were trying to get rid of their royalty. The Russian Revolution came later. But the thing is that one of the things they wanted to get rid of too were the units associated with royalty. And they wanted scientists to be able to talk from one country to another country, because we were trying to grow science. And so scientists would have different units. So the length of a foot was different in every country. And a foot used to be established as the length from the elbow to the wrist, I think, or maybe the top of the hand for a king. So it would change with each king. I mean, it was ridiculous. And then every village you went into had its own set of units. So you would go into one village and order a cup of beer, and it would be a certain size cup. But then you go to another village, pay the same price, but you get a different size cup. And that was a real problem, especially if you were like, maybe not beer, but think grain, that you were making bread for your family. And you would have different measurements in different places. So the idea was to standardize so that everybody would know when they ordered a certain amount of grain that they were getting the amount that they were promised. So anyway, so one of the first things was the length. So the length is the meter. And instead of relying on a king, they wanted something very scientific. So they said, well, we now pretty much know the size of the Earth, which is round, by the way, roundish. And they said they made the length, the meter, 1/10,000,000th of the distance from the North Pole to the equator. Now, you don't want to measure that every time. And nowadays, it's defined in terms of the speed of light, how far light will travel in a vacuum in a certain amount of a second. So it's 1/3,000,000th almost of a second. So it's very short. But we can measure that sort of thing. Now, so what they did was, yeah, they pretty much knew the distance between the equator and the North Pole. They divided that into 10 millions, and that's your meter. And so anyway, of course, looking here, we have A and B. And which one of those, so get ready to chat here, I'm going to ask questions, is A or B the meter stick? Okay, so send me an answer. I'm waiting. Which one is a meter stick, A or B? Oh, come on. If you guys don't answer, that takes all the fun out.
B.
B. Okay, great. Okay, so yeah, you can chat it or just yell it out. That works too. Okay, good. Okay, so yes, it's the meter stick. And one way you can tell is that, of course, the inches are usually done in halves and quarters and eighths of an inch. And the metric system, everything is in tens, which makes it a whole lot easier to work with. And so you can see how there are, of course, 10 little divisions between each centimeter. The other thing is, of course, a centimeter is smaller than an inch. In fact, there are, oops, wrong pen. Oh, somebody was saying they were having trouble, they wouldn't be able to print out the worksheet, but the worksheet, you should be able to draw on it also, so we'll talk about that. But just like right here, I'm just using the draw. You can do that on your worksheet too. So just pick out a pen and you might be able to answer the questions just by scribbling on the document and send it back. Yeah, it's going to be a little messy, but you know, there's a coronavirus out there. That's okay. Okay, so where was I? The 1 inch equals 2.54 centimeters. So in other words, there's about 2.5 centimeters. So about 2.5 centimeters in each inch. And so you can see that works pretty well. And the thing is, this is exact. It's exactly 2.54 centimeters. Now, how did they manage that? Well, they actually shortened up the inch a little bit. In fact, I was pretty excited to find out this was done just a few years before I was born. I don't want to give that away too much. It was done like a decade before I was born. Okay, so about 1960, you have all of a sudden the inch changed, which is pretty cool. So if you've got an old meter stick or yardstick from your grandparents somewhere in the basement, you might check it out and see if it actually looks any different than a newer yardstick, because basically inches were changed. Not much though, but they were changed so that this would be an exact amount. So you can put 3 lines here. 3 lines means equals, definitely equals, exactly. Okay, so anyway, but we're not going to do a lot of conversion, like I said, but it is kind of interesting that inches were changed to match the metric system. And in fact, that's when you can say, well, we're really using the metric system now, we just don't always know it, because all of our units have been redefined in terms of the metric system. Okay, so that's the length. Now, the thing is, in, of course, science, we sometimes measure really, really big things, like here, distance, okay? And we sometimes measure really, really small things. So that's the distance to a large galaxy. The Andromeda galaxy, which will crash into our galaxy in about 4 billion years, so don't worry about it. And the diameter of a proton, very, very tiny, right? Now, of course, if we tried to write this with a bunch of zeros, it would not fit very well on the page. 22 zeros would be crazy, right? So, of course, we use this notation, which you may recall is called scientific notation. Now, we don't do a whole lot of it in this textbook, but we are, of course, going to have to use it sometimes. Sometimes we have really big distances. We're going to have the speed of light, which is 3 times 10 to the 8th meters per second. We're going to have the size and mass of a proton and stuff like that. So yeah, so scientific notation is going to be in there, but you really aren't doing a whole lot of calculations with it, except when we have to use it for the speed of light. Okay, so anyway, most of the time your answers are going to be pretty regular units. Okay, so anyway, so we don't really know the metric system very well often here in the United States, but a meter, or the height of a person, is about 2 meters, right? The height of a table is about 1 meter. Okay, now hopefully you have a meter stick or a yardstick at home, because that's going to help you with the lab that you're going to be doing. We're going to talk about it. Okay, let's see. Ooh, 10:50. Oh, probably we should start talking about the lab. Let's see, what time do you guys get out? Oh, no, you don't get out till 45 after now, so we've got a little more time. Okay, so we're going to keep going for another 10 minutes on this and then do the lab. Okay, so what about units of mass? Well, units of mass are the kilogram. Now, the kilogram is currently defined as the mass of a platinum iridium cylinder that's kept in the International Bureau of Weights and Standards in France. Okay, now that movie I said to watch, the video about the roundest object, is about the idea that we want to replace this kilogram, which when you watch the movie, you find out there are like 8 of them, and they're not all exactly the same. They're standard, but they get old, and gradually over time, their mass changes. But let's just talk about mass for a minute. So this in here is the little kilogram that's kept safe under all these jars so that it doesn't get oily from your hands or anything like that. You can only touch it with these special tongs. And so that's kept in France. But of course, here at the United States, we have our own Bureau of Measurements and Standards. And so we have our own kilogram sets. But yeah, they want to get away from that. And they want a better definition. So now, one thing is, in the United States, we don't use mass a whole lot. We tend to use weight. And guess what? They're not the same. So this is a video, the graph, which is about this difference between what the kilogram is. Okay, so that's a very interesting one too. I'm not sure if I have that on the list. Anyway, fantastic show. Anyway, so I'm sorry, it's exciting. So let's talk about mass versus weight. A mass, so here's a kilogram. Okay. Mass is an indication actually of inertia, we're going to find out. When you try and wave this kilogram around, it's pretty hard to do because it has a fair amount of mass. It has a kilogram, 1,000 grams of mass. Okay, whereas if I take this rubber ball, which has much less mass, I can wave it around much faster. Inertia is a resistance to change in motion. This ball doesn't have much resistance to changing its motion. It doesn't have much mass. Whereas the kilogram has a lot more mass. It's a lot harder to change its direction. Okay, so that's really where mass comes in. But mostly here in the United States, we think about weight. Weight is how much gravity is pulling on an object. So the force that I'm feeling on my hand right now, that's the weight. But when I shake it back and forth, then that's when I'm feeling the mass. Now, unfortunately in this country, we don't talk about mass very much, and that's one of the probably things that stops students from really enjoying science is all of a sudden there's this new stuff. Mass relates to weight. The bigger the mass is, the bigger the weight, because the more gravity will pull on it. But it's not exactly the same. Okay, so let's look at some of the differences here. So the system that we use in the United States is called the British system because it is leftover units from the British Empire. And we got rid of the king, but we kept the units, strangely enough. Okay, so we actually use the British system. Okay, so I'm going to make a little chart here. Okay, so there's the British system and there's the metric system, or Système International, the international system of units. Okay, and then there's mass, and then there's weight. Okay, in the British system for weight, we use the pound. I'm going to put LB, okay, for pound. And in the metric system, the unit for weight is a force, and that's going to be measured in a unit called newtons that we'll be talking about soon. Okay, that okay, so mass. Now, in the metric system, mass is the kilogram. But you can see I've got an opening here in the box. What's the British system mass? Well, there is one. It's called the slug. This is the unit of mass for the British system, which most of us have never heard about because we just don't use it. I mean, think you could use it on a birth announcement. You could say, "Hi, we've just had a child. That child is 0.3 slugs large." We don't do that. It's a stupid name. Anyway, but of course, it's a slug, a mass of metal. Anyway, the slug is about 32 pounds. So yeah, you could have a whopping child, like mine, if they were a third of a slug. And if you want to know how many slugs you are, so what is your weight or mass in slugs, then just take your weight. So let's say you're about 120 pounds, divide by 32.2 pounds per slug, and that's going to give you your number of slugs. So you would be about 4 slugs. Okay. All right. 4 slugs. All right. So anyway, yeah, so it's pretty amusing that that is the unit that fits in this box. The British system of mass is a slug. Okay. So you learned something about your own system of units that you probably didn't know before. Anyway, I don't have a slug to show you. 32 pounds. I did not bring that from the college. We don't even have one there. Okay. All right. So let's go back up and look at time then. So time is the second. And 1 second is the time for radiation for cesium-133 atom to complete 9 trillion, I think it is, oscillations. So it's an atom that actually vibrates. It changes its orientation. It's like a triangle, a pyramid that flips in and out. And it does that many times. Okay, so 9 trillion times in a second. Now that's the new way of counting it. And to do that, you have to have a special clock, of course. But the second pretty much has been the second, the same one it has been for a very long time. For people, it's just been redefined as the number of oscillations. So there's an atomic clock. So this is at the National Institute of Standards in Washington, D.C., or somewhere around there. And it's this giant clock where they track actually this little cesium atom vibrating. Now, over here on the right, I've got the Galileo pendulum clock, because there were no clocks really available to Galileo. He did all his science work without an accurate way to time things. People didn't really have a good way. They would say, okay, when the sun's at noon, you know, or an hour past, you know, but it was pretty approximate in those days. And, you know, they would sometimes use candles. So you would have a candle and it would be marked by the hours. But of course that depended on the candle wax, and it depended on the temperature of the room probably a little bit, and it depended on the wind that was blowing by. So it wasn't very accurate. Galileo actually invented a water drop clock where water would drip out of a spout, and he would keep time that way. But again, that's not very good, but at least it was a constant drip, drip, drip of water, so he could count things. But it wasn't really good. So Galileo invented the first pendulum clock because he noticed something about pendulums. He was sitting in church one day, and it was a big cathedral and in Italy, and there were these lanterns hanging from the ceiling. And it was so windy in there that they were blowing back and forth in the wind. And he noticed that the ones that had short strings, chains, went at a quicker pace than the ones that had longer strings. Okay, and so he figured out that he could actually use that to keep track of time. And so he designed a clock, but he never got to build it because he was in jail, and or under house arrest. And so people built it later, but he figured out he could use a pendulum to keep track of things. So how did he do his experiments? Well, sometimes he used his own pulse for a clock. So he when he was studying in the cathedral, you know, he was sitting in church looking up at the lantern swinging, and he kept track of their time with his pulse, because your pulse is about once a second. And so he would actually count the seconds with his pulse. Anyway, so yeah, so he was handicapped by not having a clock. All right, so, and there are very long times, like the age of the universe. There are very short times. The time between a heartbeat is about 0.8 seconds. Human reaction time is about 0.1 second, which sometimes in class at this point, I pull someone out and ask for a volunteer anyway, and I drop a dollar bill between their fingers. It's an old thing. But if you drop a dollar between your fingers, it's actually hard to catch if the other person doesn't give you clues. So because the dollar bill falls pretty fast, just like many things fall pretty fast, and our reaction time isn't always enough to catch it. If somebody releases it and you try to catch it, try this on your little brother or sister or another volunteer and see if they can catch it. You may or may not want to promise them the dollar bill. You can just use a piece of paper if you wanted. But yes, you got to have a little patter going, so that they're distracted a little. Don't let them know when you're going to drop it. Just all of a sudden let go. And it's amazing how often they will miss. Their hands close, but it's too late. Okay, so I did have a student who caught my dollar bill recently, but usually they don't. Okay, so anyway, so there are big masses also and small masses. Human beings are about 70 kilograms, so we will use a range for human masses, usually between about 50 to 100 kilograms. Okay, so let's look at the metric system, which you probably look at this page and go, oh no, we're not going to use all of these. Okay, so some of them you probably should know, which like centi. Okay, so centi, there are 100 centimeters in 1 meter, right? Centi means 1/100th. It's supposed to be like a dollar, right? Like 100 cents on the dollar. Oh, and I forgot to tell you the pirate story. Why don't we have the metric system here in the United States? Well, we were supposed to have it. Thomas Jefferson was trying to get the metric system. He got it for the money. So Thomas Jefferson is the one who said, hey, let's not use shillings and pounds and stuff like that. Let's use a unit that's based on tens. Otherwise, you'd be stuck with shillings, which is like 14 and stuff like this. Thank goodness we don't have that. So he got the dollar through. But then what was happening was the Bureau of Standards in France was sending across the ocean a sample kilogram and a sample meter, and then Thomas Jefferson was going to present that to Congress, and we were going to all agree to have the metric system. Well, unfortunately, the ship was captured by pirates, and the kilogram and the meter were taken by the pirates, and they never made it to the United States for many, many years later, and by that time, Thomas Jefferson was no longer president. And that's actually the reason we did not get the metric system, at least one reason, the pirates. Okay, so a friend of mine, Treva, is a pirate. Well, she does pirate demonstrations and pirate talks and stuff like that. And she may come and do a talk for one of our classes on Zoom. Anyway, but she's like, oh no, pirates, they were really great. They had the first democracy and all this, which is sort of true, but they did ruin the metric system for us, so I can't say they're all good. Okay, so anyway, so pirates, write me a paper on it, earn extra credit. Okay, not pirates in general, pirates in the metric system. Okay, all right, so centi means 1/100, and so like I said, there are 100 centimeters equals 1 meter, of course. Now, this one you will sometimes have to transfer from centimeters to meters. It's one of the few conversion ones you'll have to do. And that's because often you will measure things in the lab and you'll measure it in centimeters. But if it's going to work in a formula, for the formulas, you have to have meters. Okay, so sometimes you will have to convert, and I'll show you more on that. But basically, because they're 100 centimeters in a meter, if you only have 80 centimeters, then that's going to be 0.8 meters. Okay, and the way you do that is the decimal point. You have to say, okay, well, what's going to happen? Basically, you have to divide by 100 that moves the decimal point over 2 places. So if you have 32 centimeters, move the decimal point 2 places, and that's going to be 0.32 meters. You can put a 0 in front if you want. Anyway, so, but I don't require it. Okay, so that's how you would go that direction. And that's usually the direction we want to go because we actually made the measurement in centimeters. We need it in meters for the lab, for the equation. Okay, so keep that in mind because we're going to do something in centimeters for the lab. But now it's time. Let's go look at the lab. Okay, so we will pick this up and continue on this a little bit later, or I'll just make a video on it. Okay, so we've covered a little chapter 1. We've covered some metric system. Now we're going to look at the lab. Oh, Frank says the volume is cutting out. Anybody else notice that? It might be, did I get farther away sometimes? I'm not sure. Okay. All right, get rid of this. And, oh, by the way, if you want to put a picture up, that would be nice. To put a picture up, I guess you put one separately up on Google. But also you can put a picture up in your D2L, which is good also. And so anyway, we will talk about that more later. But thank you, Kylan, for putting a picture up. Okay, at least I can see someone is here. Okay, as well as names. Let's see. Okay, the volume is fine. Maybe check your connection. Okay, so maybe Frank needs to check his connection. Okay, let's go to the D2L again. Okay, and as I said, we're going to start doing the lab. And so the first part of the lab is called variables. And you're going to learn about variables and then collect data to use in the second part of the lab, which is graphing. And as I said, we're going to cover that on next Monday. Okay, so labs aren't always all on Thursdays. Sometimes they carry over, especially with this new format. Okay, all right, so I'm going to pull it, instead of clicking on here, which takes a while, I'm going to pull it up from my box. Oh, where is it? I kept it in. It's my online APS labs. There it is. Which, yes, there are more labs. But some of them are still being written and adapted, so they're not all in this file yet. All right, so let me get rid of some stuff. Okay, so in this lab, there's an introduction to the idea of variables. And so usually we think of variables, we think X, Y, that sort of thing. But a variable can stand for many things. And in fact, the definition of a variable is a quantity that can take on a set of values. So that's why we can say X and Y in mathematical equations, but also in science we have variables. So like Galileo was looking at the pendulum swinging. What was his variable? The length of the string, right? The length of the chain that was holding the lanterns. That really was his variable. It took on a set of values. And then he timed it. That was another variable. Anyway, also though, variables don't have to be quantities. So it can be a quality or description. So if I were describing a musical instrument or a drum, I might say, well, it's a big drum, or that's a small drum. Or I might talk about the sound they make. So one drum might make a sound that is, right? The drum might be a little rat-a-tat-tat sound, usually for a small drum, or it might be a big, deep booming sound. So sound could be a variable. And you can describe it. And sure, we can find some mathematical way to describe it, but most of us aren't going to describe a sound or casually something by math. We're mostly going to go for big, small, and and things like that. Or we might describe sounds as pure or blaring. Okay, so what's the difference between a trumpet and a flute and a piano and a guitar? They all have different sound qualities. So they might all be playing the same note. So when an orchestra warms up, they're all trying to play the same note, but they all sound very different because they have different qualities to them. And we'll talk more about that when we talk about sound. And so anyway, so those are called qualitative variables. Qualitative variables are more descriptive. Now, then there's also quantitative variables, and that's where the numbers come in, right? So quantitative, quantity, has to do with is what that variable's about. Now, musical instruments can be the length of the strings, the width of the drum head. You could actually measure all these things. And so if you're ordering a flute or something, you would say, okay, this is how many inches it needs to be. You're actually giving some sort of number that helps you to understand how big it's going to be. And that tells you what the sound is going to be like. Now, sometimes variables can be measured in qualitative and quantitative. So pitches of sound, you could say high-pitched or low-pitched. But pitch, which is also a frequency, can be measured. So a high-pitched sound might be like 12,000 hertz, and a low-pitched sound, that would be like 50 hertz, okay? So yeah, so high-pitched versus low-pitched. Anyway, so when we are doing experiments, sometimes we do a lot of measurement, especially in physics and chemistry, but we also do qualitative things. And not so much in physics as much as you might think, but think about a geologist. They're describing a rock. And the rocks, you can measure some things, but other things, you just have to have a word description for it. Shiny, okay, there is actually a way to measure shininess, but mostly you're saying, okay, I've got some metallic objects, they're shiny, and non-metallic objects usually are more dull, and that's usually good enough to get by with. Anyway, so what you're going to be doing is you're going to fill out this table. And again, if you aren't able to print it off, you can do like what I'm doing. You can use the draw to get yourself a pen, and you should be able to fill it in. See, t-shirts are qualitative. But waistband size, that's quantitative. So you can do that, right? So anyway, so you can fill it in using, if you can get Word, even if you don't have a printer. Okay, or you can print it off and make exit, write in the blanks, or you can fill it out online in different ways. So whatever you can do to get it in, that's fine. Okay. So this is a picture of junk, well, stuff in my collections around the house. But I've got, some Legos and erasers and marbles and little animal figures, which I like a lot of, evidently, and a golf tee and washers. And I described some of them because they're a little unusual. Like I've got a ball of amber here. Here's some amber. And it's reconstituted amber, so this did not cost $1,000. What it is they melt amber that's not very good, and they remelt it till it looks pretty again. Anyway, so there's amber, there's some cork, there's a conker. A conker is actually the seed pod from a plant, a buckeye. And so there's other things in here. K2, this is one of my favorite rocks. I have favorite rocks. K2 is a rock from the mountain K2, basically. And it has these blue spots. Pretty cool. Anyway, so I've got some descriptions there for unusual things. And then the idea is that we're going to group these by a variable. So variables and values. So I'm sorting things into piles. So here I've sorted it by color. That makes color my variable. And my values, I have a blue-green pile, I've got a white pile, a gray pile, and red and clear and so on. So I divided it into some piles, and I could have made a separate blue pile and a separate green pile. So if you were doing this, you might separate it out more. I've got a multicolored pile, okay? And the idea is that these colors, these groups that you put them in, those are the values. So variable is color, white is one of the values, red is one of the values, okay? And color, of course, is qualitative. But of course, we could use quantitative here. We could make sort of a pile that separates these into things that are smaller than 2 centimeters, things that are 2 centimeters to 5 centimeters, or so on. So you could have different piles based on measurements too. Or you could just have small, medium, large. That would be more qualitative. Now, so here they've been sorted again, and I sorted them into piles of animal shapes and sort of round objects. Some are round and flat, so I sort of combined those. These are floppy, loopy things, okay? So anyway, I tried to figure out shapes. These are all geometric shapes. These are pointy. Anyway, so the thing is that I sorted them out. These, I didn't know what to call them, so I call this undefined, okay? So anyway, so I sorted them again, all right, by shape. Now, you may not agree with my you say, I could do a better job than that. Well, now's your chance, because what you're supposed to do is imagine a variable that you would sort them into and what values you would have. So the values are, what piles would you sort these into? And so you would, resort them. You could do them by size. You could do them by material. Okay, I didn't do that one. You could do, some people come up with some interesting things. So how would you sort these objects? Okay, so I just say to do one. Okay, and so you're supposed to list that in there. Now, if you and of course you should be able to type things in. My variable is origin. And that would be qualitative. And some of these are from plants, some are from animals. Okay, I don't think I actually have any that are from animal. Oh, yes, I do. Seashells. Seashells. One seashell. Okay. And so on. Okay. So anyway, so you can type stuff in, right? So you don't have to print this off necessarily. Okay. So what you're going to do then at home today, or whenever you decide to do it, is to get 20 items from around your house. So they could be any little collections you have. I was collecting up another, I was like, okay, how many spheres do I have? So I've got spheres, lots of spheres here. So balls, I'll bet you've got basketballs, baseballs, footballs in your garage that you haven't looked at in a while maybe. Anyway, so lots of spheres. You might have a jar of coins, okay, and you might have, other things, so Legos, whatever you've got a little collection of, then you can use that for sorting. Now, coins are pretty obvious, but that doesn't mean they're a bad thing to do, because guess what? You're going to have to figure out 3 different ways to sort those. And even coins, you can sort 3 different ways, I'll bet. It's not all just quarter, dime, and nickel. You might have some Canadian ones, but you might also sort by color, or some of them are, have an edge and some don't. So 20 of the same kind of object. No, it can be like mine. It can just be a collection of junk. So, so how many groups? At least 3 groups would be good. So anyway, so it doesn't have to be the same kind of objects, just small items. Okay. All right. So then you're going to make them into piles, have at least 3 variables, 3 values. Okay. So, and you're going to do 3 variables, and then each of those should have at least 3 values. So like if you've got red Legos, blue Legos, and green Legos, there you go. Anyway, so you're supposed to take a picture of your pile, and you should be able to like save a picture. So you can take a picture with your phone, email it to yourself, save it on your computer, and then insert it, which is what I do with these pictures. How did I get them? Well, I took a picture with my iPad, but yeah, then I email it to myself, and then I save them in a picture file. So my lab pictures, and then so these are some of them in your homework, lots and lots of lab pictures, and actually some of these are in the other one, physics lab pictures. So anyway, so take a picture. Now, once you have a picture, you can write on it like I did too. If you want to write on it, at least I've got Word and stuff like that. And usually you can take a picture and it will appear and then you can edit it. Sometimes it's weird how it doesn't want to do it. Okay, try it again. Okay, so go to edit. So you can do edit and create, or do this. You can crop it. So if you want to get rid of stuff that's around there, you can change the size, you know, just to the stuff you want. And you can adjust the lighting. You can straighten it, you know, and you can adjust the lighting on it. So you're like, oh, it really needs to be brighter so the teacher can see what I did here. So you can try that. Also, though, you can crop and rotate. Da, 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 da. Adjustments. Where did my edit go? I'm like showing you how to do this. Edit. When you go edit, then that allows you to draw. Okay. So anyway, so yeah, so you can, you know, say, okay, here are all the spheres. Okay, got those. Really bad handwriting here. Okay, and I've got a touch screen, so usually I just draw right on the screen. And so it helps to have a pen, or you can do it with your finger. So okay, here's all the spheres. All right. So anyway, so you can do that. So you can document it too, stuff like that. And then once you're done with it, save a copy, and then you should be able to just either cut and paste or insert it into here. So cut and paste, once I had it up there, I could have copied it. Maybe I can copy it from here. Yeah. Copy. And then insert. Sure. There it is. Okay. And then hopefully you might want to reduce the size. There you go. Okay, so now you've got proof. So you've got to put in some words and pop in some pictures. Now that's going to spread this down further, so that's okay. It's going to make it big. That's all right. Okay, so anyway, so that's the first part of the experiment. You're going to do this at home and gather objects and do that. Now, the other thing is a discussion in here about independent variables and dependent variables. So the independent variable is what you manipulate or choose. And so if I were doing a pendulum, I might be changing the length of the string. So I've got a ball swinging. Sorry, I didn't prepare one beforehand. So the ball would be swinging on a string, and I could change the length of the string. You're going to do this lab also in the future when we do waves. Now, what you might be measuring is the time. Like Galileo was interested in how long it would take for that pendulum to swing. That would be the dependent variable, because that's the one that depends on the string length that I chose. So independent is the one you choose. Dependent is the one that results. So you choose a certain length of string, you get a certain time. So, and so there's discussion here. So Galileo did this a lot. So he would, sorry, that's my clock, telling me it's 25 after for some reason. Anyway, so Galileo rolled balls down ramps, and the higher he raised the ramp, it was at a steeper angle, then the acceleration got greater. You guys, we may be doing this lab too. But you have to get good data. So you always have to control some things. So you wouldn't want to do the experiment on a wet day when it's raining and then think, okay, that'll be the same as it will be on a dry day when the ramp is dry. That doesn't make any sense. So you have to control some things. And, you know, what kind of ball do you use? That matters too. And do you just switch balls in the middle of the experiment? I hope not. So things like that are called controlled variables, right? They're things that you keep the same during the experiment. And so, anyway, so there's discussion of that. Okay, and then there's a question to answer. So every time it says question, you're supposed to answer it. So there's a question. And if there's several questions, you answer all of them. Okay, and then you're going to actually do another experiment at home. So you're going to need some balls, some bouncy balls, something that will bounce, okay, a little bit. And what you're going to do is measure to see how high the ball bounces. So you're going to drop a ball and then see how far it bounces up. So that, of course, is different for different balls. So there's some data I show you as an example. I got that data with this ball, even though I said red ball, just because it was easier to write red than multi-stripy ball. Anyway, so you drop it, and when it bounces, this one doesn't bounce really well. It only comes up about half high. Let's see if this tennis ball does any better. Not much better. It's probably not very good. Tennis ball. Some balls, though, should be doing a little better, maybe. Okay, now one problem is they're on this table. They probably would do better if they were on a concrete floor. So that's something also that I have to do, is pick the right surface. Anyway, so what you're going to do is exactly what I was doing. Find some bouncy balls. Find your best bouncy balls of different kinds. And you're going to drop the ball, and it'll bounce back up. And you're supposed to keep track of that measurement. So I suggested that you put a piece of paper on the wall, tape some paper on the wall. So you can drop a ball, so mark that, drop the ball, when it bounces back up, mark that. And that way you don't have to actually be trying to measure it at the same time, because probably a lot of you do not have a meter stick at home. But if you do, then this is helpful. You could also use a tape measure. But if you've only got a regular ruler, then you're going to be wanting to drop the height from like 3 or 4 feet. So you're not going to want to, you know, the ruler's not going to be much help there, but you can measure it afterwards. Anyway, so yeah, so you can use a measuring tape. If you've got a meter stick, which I had, okay, what did I do with my meter stick? Okay, so my meter stick has temporarily left me. That's on. Anyway, I'll use this, which has a meter stick on it. Anyway, so the idea is that you could tape your meter stick to the wall, drop your ball, and then see how high it bounces. So you could eyeball it instead of marking it. So you can mark it on paper or just drop it. Now, when you mark it, just mark from the top. That's the easiest to see, right? So you don't have to try and say, okay, where's the middle of the ball? It's the top of the ball we care about. You know, that's the easiest one to see. So it comes back up, mark where that is. So you can use a combination of, you could have a tape measure or a meter stick and a piece of paper. So you can mark on the paper quickly. As the ball comes up, you can mark it. Now, you may want an assistant for this. So maybe there's someone in your house who will help you to drop the ball and you do the marking, or vice versa. Anyway, so yeah, so get some balls, perform the experiment. And then you're going to do that. Now, if you want to get real fancy and use a video camera, there's a videotape here we're going to watch, a YouTube video, which we are going to watch for the second part for a reason. So when you do the graphing, but you could watch it now too. So he uses the video camera to get very accurate ideas of where the ball is. So you're going to do that. You're going to do 5 trials for each ball. So you're going to have 2 different balls. And so they shouldn't be 2 tennis balls, 2 different balls. Unless they're 2 tennis balls where one is much worse than the other. And I will allow you to use inches because sometimes people, maybe your tape measure is only in inches or your meter stick is only in inches because it's really a yardstick. Anyway, so yeah, so if you have to, you can use inches. Okay, and so then you're going to take a picture of your setup. You can also make a short video. We might actually put those on, oh, not mashup. There's some video thing. Okay, anyway, and answer the questions in the following pages. All right, you don't have to make a video of every trial, just show your technique. Okay, all right, and then you gather the data, you answer questions, and then you're going to use this data for the second part where you're going to graph it. So I'll talk about that on next Monday. But of course, if you want to go ahead and do the graphing and follow the lab 1B, you can go ahead and do that too. Okay. All right. But it's not going to be.
When is this lab due?
When is it due? You always have at least a week. I'm making things due on Sundays. So that means this won't be due till next, not this coming Sunday, but the one after that. Okay. And so that's when it's due.
Are you also doing the graph lab?
The graphing lab we're going to talk about on Monday, but what I was saying was you could go ahead and do it if you want. If you just really want to go ahead and graph the data. It has questions also, but we will go over it on Monday. Okay. All right. So anyway, okay. And so that's the lab. So you guys have about 12 minutes. You can start working on it or take a break before your next classes and work on that this weekend or whatever. Anyway, so it was nice to meet you this week and hope to see you next week. And I'll let you know, hopefully by Sunday night at least, what the whether we're going to try Zoom. Have you guys been using Zoom for your other classes? Has it been working okay? Do you prefer Zoom to this setup? Let me know. Okay, so you can send me an email. Because Google Meet's pretty good. Okay, so anyway, so let me know if you have an opinion. Oh, you like Google Meet a little better. Okay, all right. Anyway, so yeah, and the nice thing about Google Meet again is it's so easy for you to get the videos and it's so easy to just schedule it in your calendar, which you can do with Zoom too, but it's easy for me to schedule. Okay, all right. Okay, so anyway, Google Meet is easier. Yeah, it just plain is, I think. Okay, all right, then we might just meet in Google Meet for the rest of the term. I'll think about it. I'll play with Zoom some more this weekend, and see if there's some reason for me to like it better. Also, do you guys want to have a Sunday office hour? So like I could have a time when I would be available on Sunday. Is that something that you would be interested in? Otherwise, it would be mostly after class. So Kayla says yes. So especially if I'm making things due on Sunday. Okay. So yeah, so I'll probably set up a time on Sunday. So I'll just try to be around. I'll probably put it on Google Calendar. And then you guys can just ask questions on Google, or you can chat me with D2L. Okay. All right. Okay, I think I can do that. Okay, good. All right, well then have a good week, and I hope things are going well. There's a discussion post that you were supposed to do. So I mean, it's not overdue yet, but the first discussion post was about whether you would like to go back to the good old days. So far, looks like most people say no, but almost everybody who turned in something also was a woman, and definitely for women, I think when we look back in the past, we say, no way would we want to be back there. It's like there was, if you've ever read Lord of the Rings, there's a wonderful introduction in the front of it that says, would you go to Middle Earth? And it says, sure, most people would go to Middle Earth like a shot. And then it's like, when you read it, when you read the women, what happens to the women? They're like dying in childbirth, getting tortured, and all this stuff. And it's like, you know, Middle Earth may be great with all the magic and stuff, but I'm not sure I want to go back to, again, not having a medical system. So anyway, so yes, so there's the first post. And then there is the second one, which is about Galileo. So we've covered enough on Galileo. You probably could start doing that one too. So there are actually 2 discussions that will be due. But again, they're not going to be due till, well, the first one you probably should finish up by this Sunday. And the second one won't be due till the week after. Okay, labs aren't due till next Sunday. What is going to be due this upcoming Sunday? Well, I was just saying that if you could get that first discussion post done, that would be good. So the prologue one, but the second one won't be done till the Sunday later. And what else is due? Well, you need to do the homework for the prologue, but again, usually I give you a whole week. So I guess from Monday to Monday, I guess this Sunday would be pretty much a whole week for that. So from Monday to Sunday. But homework, as you hopefully read, is, you know, it's not, it has a due date, but it's not actually overdue until the test. So the prologue homework, the chapter 1 homework, I may put due dates down and you should do them, but they're not late if you get them in a day or 2 late. Okay, so what is actually due this Sunday? Try to get that discussion in. Oh, and don't forget the tech check quiz. That one has a date too, but I think you've got a couple of more days on that also. Okay, I'll try to make a list. So I'll put it in the announcement, what's coming up and what's due, as well as putting dates on things. So that's work I've got to do. Okay, well, have a good weekend. The rocket lab. Oh, yes, the lunar lander. Yeah, so keep trying to get the lunar lander lab to work. Mostly that's an exercise to see if you can get those simulations to work. So yes, keep trying to work on that because it's really something you need to know. Can I make this work? Okay, so thank you. Discussion, tech check, prologue homework, and lunar lander. Fantastic. Thank you, Kayla. So that looks like a good list. Okay, so here I'm saying not much is due. It's not, you know, I'm really easy about due dates. In fact, that's part of the problem. Usually I'm like, oh, turn it in. And the problem is when you're on the computer, you have to actually put a date in. So I don't like that. Okay. So anyway, so I would try to make the dates as loose as possible, but the computer isn't going to allow me. Okay. All right. So that sounds good. Thank you for Kayla. Okay. Good night or good day. Anybody want to stick around, do homework? You can do that or ask questions.
Hi, I would like to go over the syllabus since I wasn't here. I was at class last.
Okay. All right, great. Okay, so let me pull up the syllabus and we can talk about that. And I'm going to turn the recording off, I guess. Okay. Let's see.